You can start. Thank you. Sorry. Yeah. So now we would like to prove the main result that systoles of closed hyperbolic manifolds are dense in the positive reals in every dimension. And really, the proof is based on the following uh, observation. And in fact, really, this is our contribution in this observation. So this is our only contribution to to the I mean, all the other tools were sort of there, but it's very straightforward. So the observation is the following. Suppose we have a hyperbolic manifold, maybe closed, M, with the following properties. So we'll want M to contain two disjoint there are several adjectives. So closed, embedded, two-sided. This is a technical condition that you can ignore. Totally geodesic hypersurfaces. Call them sigma 1 and sigma 2. And suppose that the systole of M is larger than twice the length of a shortest orthogeodesic segment in M. Maybe I should give it a name. Segment omega in M with endpoints on and orthogonal to the union of these two hypersurfaces. Then the manifold obtained by cutting M along sigma 1 and sigma 2, and then doubling along the boundary. This might be disconnected manifold, but we don't care. It's certainly, I mean, once you double, it's without boundary. And it will have systole precisely twice the length of omega. So, let me try to draw a picture. So we take a hyperbolic manifold M with two totally geodesic hypersurfaces, maybe. sigma 1, sigma 2, and an orthogeodesic omega of minimal length uh, between them. And we assume that the systole of M is big. We can assume that it's, let's just say that it's huge relative to the length of omega. Now we cut. Once we cut, we might get several components, but we just select the component containing this orthogeodesic omega. And then we double. The picture I'm drawing is a bit simplistic, but in fact, there are no additional complications when you, I mean, and now, I mean, this orthogeodesic, I mean, the double of the orthogeodesic will give you closed geodesic of length twice the length of omega. And the claim is that it's a shortest geodesic in this double, and the argument is straightforward. I mean, if you so take a closed geodesic in this in this manifold. If it doesn't cross blue, so it's remaining entirely on one side of the manifold, then it might as well have been inside M. And so its length has to be large, right? Because we assumed M had very large systole. On the other hand, if it does cross blue, then there are at least two segments on each side, and I can pull each of them tight. And now, I mean, once we tighten, we get something of shorter length, and it will have length at least the length of omega, because it's an orthogeodesic. So we get that if a geodesic crosses blue, it has to have length at least twice the length of omega. Is the observation clear?
Yes.
Clear.
So the very convenient thing about this observation is that I mean, if we can find a manifold M that satisfies one, that has the first property, then any finite cover, I mean, well, any cover will still have that property, but any finite cover will still be a closed manifold that retains that property, that still has that property. And remember that we can make the systole as large as we like by passing to finite covers, right? So now the game is just to find manifolds. So and now the goal becomes given say L and epsilon positive, well, and N. Find a closed hyperbolic manifold M of dimension N with two disjoint closed embedded two-sided totally geodesic hypersurfaces joined by an orthogeodesic so, well, if you want, okay, such that an orthogeodesic with endpoints on, sorry, I should have given them names, sigma 1, sigma 2, with endpoints on the union has length um, within, sorry, of minimal length, of minimal length as length uh, within so again we're just trying to find um, uh, a manifold with disjoint closed embedded totally geodesic hypersurfaces so that I mean with almost prescribed length of shortest orthogeodesic. That's essentially what we're looking for. And then we know that if we find such a thing, we can just pass to finite covers so that the second um, condition holds, and then we cut and double. Um, so that's the strategy. And now the question becomes, how does one do this? And in fact, it's I mean, it's not. I mean, the details are important. So first of all, maybe I'll describe how one might try to do this in dimension 2. So and in fact, in dimension 2, I don't even need epsilon here. So in dimension 2, one can do the following. So first, so in the goal, the strategy will be to uh, instead of producing a surface with this property, producing an orbifold, really a right-angled polygon, right-angled hyperbolic polygon with this property, suitably interpreted, and then passing to a cover. Again, passing to covers can only help. So what you can do is take a right-angled hyperbolic, say pentagon, if you want, with or okay, maybe pentagon won't work. Hyperbolic polygon with a side length of precisely L. Unfortunately, the only picture I can find online of a tiling is of the regular right-angled pentagon, which somehow I'm going to need you to forget that this polygon is regular to understand the argument in dimension 2. But I want you to imagine that this length is L, and that maybe the other lengths are different. For example, maybe this length is shorter than L. So now what one I mean what I'm going to do is so these are going to be what I'm going to want these to project to surfaces sigma 1, sigma 2 as desired. And in order to do that, I'm going to take bananas. So there'll be bananas. These will be hyperbolic, like metric neighborhoods of width L, centered at these blue geodesics. So they'll look like this. Maybe. Sorry, this picture is terrible because I'm trying to make it not look like regular pentagons. Um, um, and now the goal is to take um, a polygon that somehow has a good geometry with respect to these neighborhoods. I don't know how. Maybe I should. I mean, the issue is that initially, I mean, um, for example, if this side length was smaller than L, in this picture it's not, unfortunately, but if it were smaller than L, then I would be able to travel. Uh, I would have an orthogeodesic here that's quite short. Um, if I mean, if I'm thinking of this thing as an orbifold, then I'm able to travel back and forth and hit. I mean, again, an orthogeodesic that's quite. I mean, I can travel back and forth between sigma 1 and sigma 2 in the quotient quite efficiently. But if I take up polyhedron that instead looks like what's a good color? Purple. Something like this, let's say. Okay, I'm not going to draw the whole thing, but I mean, you can make it compact, and the idea is that whenever you cross one of these bananas, you just do it via something that's orthogonal to one of these uh, geodesics, and then in the new orbifold that you get from this uh, sorry okay, I'm not. Okay, I should have drawn it. Maybe I'll even try to. Okay, I have time, so I'm going to try. Um, um, okay, no, I'm not going to try. Just focus on the top half of this picture, and the point here is that now I have to travel quite far. I mean, if I start out on one of these geodesics, I have to travel quite far before I hit a wall, right? Um, and now if I take the quotient of this new polygon, I mean the reflection group, the group generated by the reflections in the sides of this new polygon, it will be an orbifold with this property here. In fact, I mean epsilon doesn't appear here, so so it will give me uh, uh, a hyperbolic surface of systole precisely L. I mean, there were other ways I could do this. I mean, there are more somehow conceptual ways. I mean, basically, if I take a hyperbolic surface, again, I can make the systole huge by passing to regular finite covers. And then I mean, I can make the systole arbitrarily small by pinching somehow. And then the systole function on type Miller space is continuous. So by the intermediate value theorem, essentially, you can show that, I mean, that, I mean, S2 is the entire set of positive reals, but this is a more somehow hands-on proof, if you like. Um, and the right angles in this picture are relevant because basically, I mean, how do I describe this? I mean, the point here is that if I take any convex union of tiles in this picture, it will still give me a coxeter polygon. So it will still give me a polygon, and I mean, more specifically, it will give me a right-angled polygon. And I know that the group generated by the reflections in the sides of a right-angled polygon has fundamental domain, I mean, has precisely the fundamental domain that I think it has, right? And so I can indeed say that, I mean, if I had finished drawing this picture, that I would get a compact polygon, so compact fundamental domain, and so I get a finite index subgroup, which gives me a closed manifold in the end. So, I mean, in fact, I mean, co-compact right-angled reflection groups cease to exist in dimensions 5 and higher in hyperbolic space. In fact, an identical argument can be used, an essentially identical argument can be used to prove density of S3 and S4 using compact right-angled polygons. But there's also a more arithmetic approach, which I'll try to describe in the time I have left. So, sorry, this was kind of sloppy, but are there any questions about the two-dimensional case?
I have one question regarding you already said, but I didn't maybe understand it. Why it's 90-degree relevant? 90 right angle. Why a right angle?
Yes. So the point is that so in this picture, what you do is you try to take a union of tiles that with like nice properties with respect to these two geodesics. And more specifically, I mean, in fact, with respect to these two neighborhoods of these geodesics. In general, if you have, let's say you have, I mean, a tiling of H2 by some coxeter polygon, you don't know if you take a union of tiles, even if it's convex, whether or not the thing that you get is still a coxeter polygon. So you don't know if the angles are all integer submultiples of pi. For example, if you had a pi/3 angle, if you take I mean a union of two polygons, you might get a 2 pi/3 angle, and that's no longer I mean it's no longer an integer submultiple of pi. And then you don't know anything about, I mean, the group generated by the reflections in the sides of this new polygon that you have, you know very little about it. I mean, you know it has to be discrete because I mean it's a subgroup of the group you started with, but you can't say that it has a fundamental domain that looks. I mean, you can't say that the fundamental domain is the polygon itself, right? And here in this geometric argument, we're actually using. I mean, yeah, we're using. I mean, I think you can't even say that it's. I mean, it's not even clear if it's a finite index, right? You just know it's a subgroup. I mean, but if you don't have a fundamental domain, you can't say much.
Maybe I understand a bit. But if you have you say that if pi of for angle pi/3, you don't have you have fundamental domain start, no?
You have in fact so it's a curious fact that for pi/3 specifically, I mean, if you know that all the angles are pi/3,
for example, yeah.
Then in fact there's a variant of this argument that does work, but specifically for pi/3, there's I'm not sure if I even remember it, but there's some trick for using pi/3 that's not completely obvious, but I mean in general I mean you have angles that are integer submultiples of 2 pi, but you don't know if they're integer I mean, they're just, I mean, you have rational angles, but you don't know if they're integer submultiples of pi. You know, I mean, rational with respect to pi, you know.
Yeah, yeah.
Yeah.
Okay, thank you. Thank you very much.
Um, so maybe I'll try to describe. So in fact, I'm going to cheat. So in uh, description in dimension 3. I mean, of the proof. So I'm going to describe a strategy that really works in every dimension, but I'm actually going to there's one aspect of the proof that will only work in dimension 3, and in order to I mean to make it run in higher dimensions, you in fact need work of Beloy-Lipetsky and Thompson. But I mean the basic outline of this proof works in every dimension. So I'm going to take a very specific lattice in the isometry group of H3. So again, this is a group of isometries of H3, which I mean, if I want, I can replace the standard form of signature 3-1 with any form of signature 3-1 that I like. I can make it this form. And I will want this -7 there. I mean, I want 7. So this form has signature 3-1, clearly. In a moment, you'll see why I put 7 there. But now if I take the group of 4x4 matrices preserving this quadratic form with entries in Z, with integer entries, this will be a lattice in OF. I mean, by OF, I mean OFR. By that I mean so the quotient of H3 by this group will have finite volume, but in fact it's even co-compact, and this is because this quadratic form is anisotropic over the rationals. This is because the two addics have level 4, if I'm not mistaken, and -7 is a square in the two addics. But I mean, it's you can just accept. I mean, probably there are people here who are actual number theorists who understand very well why this. When I say anisotropic, I mean that this. I mean, if you have rational numbers that evaluate to 0 in this quadratic form, then they have to all be 0. And so, I mean, and then it's a fact that this will give you a co-compact lattice. So the quotient of H3 by this group will even be compact. And it will be an orbifold, not a manifold. But then if you pass to a finite index torsion-free subgroup, it will be a manifold. And this is the manifold that we're going to work with. We're going to try to find a finite cover. I mean, so now given, I mean, well, we want to, I mean, we want to achieve this goal, and where M will be a finite cover of this arithmetic manifold that we just described. And So let's maybe describe how do we get sigma 1. Sigma 1 will just be the projection. So this gives us a manifold, really an orbifold, but let's say a manifold n. And it, or maybe I'll call it M, and M will just become different things. M will be dynamic throughout this argument. But sigma 1 will be the projection to M of this linear hyperplane, which gives you a geodesic hyperplane in H3. And again, this projection will be compact for the same reason that M was compact. And now sigma 2 will be the projection to M of, maybe I'll call this H1 of G H2 for some G in the rational points of this group, such that the distance between the hyperbolic distance between H1 and, sorry, GH1, and this will maybe be H2. So we want this distance to be roughly L, or if we want, yeah, let's say roughly L, right? So roughly some prescribed number. And this is something we can do because the Q points are dense in this group, so we can always find such a G. But what's not obvious at the moment is that what's not obvious is this orthogeodesic fact. Like, what about? So now we have. Okay, maybe I also didn't explain that because we picked G to have rational entries. The projection of H2 will also be closed. It's just the fact that this group commensurates this group. That's the reason. But now what we want is that so let's say the distance is L. Distance is between L minus epsilon, L plus epsilon. We want, for instance, so that we know that there are no orthogeodesics with one endpoint on sigma 1 and one endpoint on sigma 2 that are shorter than L minus epsilon, for example. We'll want, for example, that we want a finite index subgroup, let's say gamma, such that for all gamma in this subgroup, the distance between H1 and gamma H2 is at least L plus epsilon. This is the translation in the universal cover of no short orthogeodesics apart from the obvious one, the one that's the projection of the orthogeodesic joining H1 to H2. This is not all we want. We also want to make sure that there are no short orthogeodesics from H1 to itself, but the argument will be very similar, and also from H2 to itself, right? And then my claim is that we can find congruent subgroups with this property. And that's because, I mean, in fact, we know precisely what, I mean, what this distance is. It's something like, I hope this is correct, but it's arch cosh of this quantity, where this is the, I mean, bilinear form on R4, R3 plus 1, given by F. And E1 and E2, let's say I can always pick them to be our integer vectors orthogonal with respect to this form to H1 and H2 respectively. But you see, since gamma preserves the form, I mean, I mean, gamma is taken to be I mean, this group, gamma is inside, I mean, this group preserves the form. It's a group of integer matrices preserving the form. This thing is just the, I mean, the bilinear form evaluated, I mean, in the norm, if you want to, or the square of the norm of E2. And so, so basically we're just comparing, we want to compare this quantity to this quantity. And in fact, here, sorry, I mean, here it's enough. And in fact, we won't be able to do better using this strategy than comparing the distance between H1 and a translate of H2 to the distance between H1 and H2. So we would like this to be true for all gamma and gamma. This is equivalent. And we still need to find such a gamma. But the claim is that we can take a congruent subgroup that does this. So, I mean, if we, here's a point that if gamma is in the congruent subgroup of big gamma of level n, this is kernel of reduction mod n, then it's easy to see that this quantity is in fact I mean, these two quantities are congruent mod n. So if I make n huge, then I can certainly always ensure this. Is that clear? Using the same strategy, you can also get that same strategy finite satisfying that the distance between hi and gamma hi is at least the distance between h1 and h2 for all gamma that don't stabilize hi. It's just a game of, picking in this capital N large enough. So you can find a congruent subgroup basically the point of this argument is that you can just very explicitly see that you can find a congruent subgroup of this initial arithmetic manifold that we have. Once we fix these two hypersurfaces, that has the desired properties. So I said that this strategy doesn't work in, that there's a part of this strategy that doesn't work in every dimension, and that's, so the fact that we have an anisotropic form of signature N1 will cease to be true. I should say a rational anisotropic quadratic form of signature N1 will cease to be true for N at least 4. This is, this is Meyer's theorem. This is by Meyer's theorem. We still have arithmetic lattices, but they'll be a little more difficult to describe, and this argument will be more challenging, and in fact it's the subject of an entire paper by Bololi, Petsky, and Thompson. So in higher dimensions, really this is the key point. This you want to ensure this property. The other properties are kind of easy, and this in higher dimensions, handled by in fact, they don't really have a statement in their paper regarding this, but if you look at their proofs, you see that that they can really ensure this this property. Okay, I think wait, how long have I? Yeah, I've been speaking for 45 minutes, so I think I will stop. Hopefully this wasn't too clumsy. Thank you.